next presentation is going to be given by Katherine Ransom. She's at the United States Geological Survey located in California. And her presentation is process-informed machine learning predictions of nitrate in groundwater used for drinking water supply in the conterminous United States. So I think, Katherine, you can get started now.
Okay, can you hear me now?
Very faintly.
Is that any better?
Better, much better.
Okay, good, thank you. Okay, so hello everybody. Today I'm excited to share with you a work that I've been working on for the past few years at the USGS as a part of the National Water Quality Program. And I'd like to first off acknowledge my co-authors. This has been a really big collaborative effort. Let's see. Try to advance this slide. There we go. Okay, so what is nitrate and how does it get into groundwater? Nitrate is a natural form of nitrogen. Sources include manure, fertilizer, natural sources, atmospheric deposition. The problem arises when excess nitrogen is applied to the land and eventually that is converted to nitrate, which leaches to groundwater. Since this is a talk about what processes can affect the concentration and distribution of nitrate in groundwater, one would be denitrification, also recharge or discharge from streams, and groundwater flow or groundwater age. Many people rely on groundwater supplied by domestic or public supply wells in the United States. Domestic wells typically consist of a single connection to an individual household, while public supply wells serve many connections. And this map shows the estimated number of people supplied by domestic wells in 2010 was about 37 million. And in 2008, about 105 million people relied on public supply wells. So previous studies have mapped groundwater nitrate contamination across the United States. The map I'm showing here is from a study by Nolan and Hitt in 2006, in which they used a nonlinear regression to predict nitrate concentration at a constant depth of 50 meters. So that was about a domestic well depth. And the red color is an area, let's see if I can use this pointer. Any red here, that was an area that was predicted to exceed the maximum contaminant level. And the US EPA has set that level at 10. And this study estimated that 467,000 people were affected by a high nitrate concentration. And there are negative health effects to drinking water with high nitrate, such as low blood oxygen in infants, certain cancers, and thyroid diseases. So the goal of this project was to update the nitrate and groundwater predictions using recently available machine learning methods and some newly available predictor variables. We developed the model at a high resolution. We had over 12,000 wells, and we predicted across variable depths across the United States. So those were based on reported well depths from domestic and public supply wells, and they varied across the United States. We also estimated the population affected at both well depths. So the way that we incorporated process into this model was not by pre-programming an equation or nitrate modeling directly into the model, but rather by including predictor variables that represent certain processes. So predictor variables for model development included 270 representations of nitrogen inputs, soil type, climate, land use, and geology. And one of the reasons that we had so many variables was due to the way that for the method that we used, the categorical variables had to be separated out into a series of 0, 1 indicator columns. And we had two general groups of process variables in our model. The first was a physics-based that was calibrated from a physical model. And these variables included characteristics related to groundwater flow and the unsaturated zone. And the second type of process variable was more empirical, and that was a group of variables called multi-order hydrologic position, and also things like just well depth. So those variables would be more like surrogates for processes that might be occurring. So here's a map of groundwater transmissivity, which is one of the 4 variables we included from a national scale physics-based model of the subsurface. That's a physical model. And the 3 other variables we included from that work were the unsaturated zone water content, the depth to water, and the unsaturated zone travel time. And the study developed these at a really high resolution of 250 meters. Each of these maps has about 125 million cells. So the way those were developed was with a numerical simulation of the unconfined groundwater system using the general equation for groundwater flow. So for all the groundwater modelers out there, that would be mod flow. And that's a water balance on a small control volume. They calibrated it with a really large data set of water table measurements. And the way they did it was one at a time for each of these 75 model domains. And then they aggregated it together at the end to make the maps of each variable. And all 4 of those that I showed were used in our nitrate model. So just a little bit more background on what those variables are and what they mean. The first one was that groundwater transmissivity. So that controls the flow of water and the capacity of the aquifer to transmit water. It's a combination of hydraulic conductivity and saturated thickness. Additionally, the long-term average water content of the unsaturated zone, so the Vados zone here, and the depth to water and the unsaturated zone travel time. So each of these can affect the amount of nitrate that gets into the groundwater and how long it stays and where it goes. The second group that I'd like to highlight, the second group of variables, are those multi-order hydrologic position variables. And these are a set of metrics to describe the hydrologic position in the context of stream order. So we had 18. There are 2 different types, and each of them had a map for one of 9 stream orders. So the first set would be 8 variables called lateral position, and those are a measure of distance from the stream. So for each stream order 1 through 9, here's the first order streams and here's second order streams. So this variable tends to increase away from streams for each stream order. And the second was a distance from stream to divide. So when they divvied up these stream orders and measured the distance to the stream divide, the variable tends to increase away from the stream or decrease towards stream confluences. And these are an empirical representation of hydrologic process. They were developed to support machine learning water quality models. So I'll show you some maps of what these look like. This is the lateral position variable. For the higher stream orders, it tends to be more of a representation of location. So distance from the coast or distance from major water bodies like the Great Lakes or large rivers like the Mississippi. And then as you go to the lower stream orders, the metrics can be interpreted in the more in the context of local processes that might be occurring. So something like stream discharge or denitrification at streams. Let's see. Yeah, so the smallest I'm showing here is lateral position 4, because beyond that, it's real hard to see. So you can see how big maps get more detailed for the lower orders. And these were also developed at a really high resolution of 30 meters. Here is the distance from stream to divide metrics. So similarly, they can be interpreted for the larger stream orders in the context of just location, where you are in the country. And as you go to the lower stream orders, it's more of a empirical process representation. So for the modeling that we did, we used extreme gradient boosting, or XGBoost. It's an ensemble tree method. Just real generally, how we developed the model was we attributed all of those predictor variables from the maps and the raster grids that I showed to the well sites to develop our training and our holdout data set. And then we developed the model, we did cross-validation tuning of the hyperparameters, and we did a variable selection routine to try to reduce some of the variables that we had in the model. And then we made predictions using 2 different depths, predictions of nitrate at 2 different depths. So here's the depth map for domestic wells. So those were the 2 variables that varied with the 2 sets of predictions that we made. So I'll go into a little bit about how we did that variable selection. What the final model had 76 variables selected, and what we did was we used a recursive backwards feature selection. So we developed a model with all the variables, and then we ranked the importance, like the global variable importance that was just discussed in the previous talk. We removed the least important variable, and then we did it again and again and again, and watched the root mean square error increase as each variable was removed. So eventually, once we start getting to fewer variables, the root mean square error started really shooting up. So we decided to allow for a 1% increase in error, and we were able to get down to 76 variables this way with only the small increase. And some of the variables that remained were all 4 of those groundwater flow model variables: the unsaturated zone water content, travel time, transmissivity, and the depth to water. And also, all but 1 of the multi-order hydrologic position variables were retained. So that's just using this completely objective method, not picking and choosing anything special. Those were all deemed to be highly important in the model. So the model performed really well. This is a map of the cumulative distribution for the holdout data. So that was data that was not used at all in model development. And the distributions of the predicted values pretty closely match the observed. So the dark blue here is the predicted, and the light blue is the observed. So one thing we did notice was the high values tended to be slightly underpredicted, and the low values tended to be slightly overpredicted. But overall, this model had good performance, especially for such a large scale model with such a diverse region. And here's what the map of domestic well, for the domestic well depth and nitrate predictions looks like. overall, there's a small percent of the United States that was predicted to have a concentration that exceeds the drinking water standards. Well, that was 1% in terms of the area. And most of that was concentrated in the central United States, so the high plains aquifer, interior Permian, secondary hydrologic region, and then things like the Central Valley and the Piedmont and Blue Ridge aquifers on the East Coast. But overall, a large population is potentially affected. We estimated about 1.4 million people might be at risk for high nitrate in their drinking water. So I'd like to thank the previous speaker for explaining SHAP. So I can just jump right into our results. So we use SHAP to assess each of the variables' performance in the model. And these values represent the contribution from each individual prediction from each variable. So what I did here was I took the absolute value of each of those and then I calculated an average. And that can be interpreted as a variable importance. So when we look at the SHAP importance, well depth was the most important. In all of the trial runs that we did, well depth was always #1. And this is the absolute value, average SHAP value here, 0.52. These units, by the way, are in log nitrate. And then because I was trying to compare an individual variable with a group, I added up the averages for these. So as a group, this multi-order hydrologic position, they weren't ranked as highly important. They were more down towards the bottom. But when I add up the averages, they contribute fairly significantly as a group. And then the subsurface variables were more highly ranked. Especially the unsaturated zone water content was number 11. So that was pretty high importance in the model. And when I add up their average values, it's slightly lower, but still a pretty good contribution. So the SHAP values can be plotted against the values of the predictor variables to interpret how the model is using these to make the predictions. So this is increasing well depth on the x-axis and the SHAP value on the y. So this would be the contribution to the prediction from each individual sample. And you can see here from the plot that as well depth increases, nitrate values tend to decrease, and especially for the much deeper depths. You're getting a high negative contribution there. But for shallow depths, you're getting a very high positive contribution. And again, these are in the natural log of the nitrate concentration. So depth is more of like a surrogate for process. It can tell us about what might be occurring, what processes might be occurring, and this tends to correlate with our understanding of the groundwater flow system and chemistry and things that are going on in the subsurface. So as the well depth tends to increase, you get more into anoxic state here. So more of a nitrate reducing zone. And additionally, groundwater age tends to increase with depth. So that might be at the deeper depths groundwater that has not had a chance to be affected by nitrate just because of the application of the nitrate to the ground surface. So water that was recharged prior to all of the intensive fertilizer use that has been going on. And the relationship between the predictions of nitrate and the process variables on the SHAP summary plots coincide with our understanding of process. for these more physics-based and empirical process variables as well. For example, the saturated zone water content, which was, here's the importance rank to the average SHAP importance here. So this is the 11th, rank number 11. So as the water content increases in the unsaturated zone, the predicted value is decreasing. There's a threshold here about little maybe 0.3, where it goes from having a positive contribution to a negative. And so that could indicate some form of maybe denitrification. In terms of the transmissivity, there's this pretty clear threshold here where above about 10, it tends to start increasing rapidly and then remain around close to 0. So really low transmissivities are having a negative contribution, and then pretty high transmissivities are contributing positively, but not as high as these other more highly ranked variables. This was ranked 23rd. And then one thing I thought was interesting was this lateral position 2 for second order streams. So those are small streams and representation more of a local type process. As you get further from the stream, second order streams, the nitrate tends to increase. So maybe there's some recharge from streams that's causing dilution or denitrification happening right next to streams. These are negative contributions right at the stream. So in summary, the machine learning XGBoost model was developed to predict nitrate at a 1 kilometer grid scale across the United States for depths relative to drinking water supply. In our model, we included variables representing process either from physics-based or empirical understanding. And from the SHAP analysis, we observed relationships between the variables and the predicted nitrate that are expected and well documented. So it was a good check that the XGBoost model is using these process-based variables and incorporating them into the predictions. And these results will be publicly available hopefully this fall. The paper was submitted to Science of the Total Environment, and reviews came back, and we just have some comments to address. And all of the data and everything, the code will be available as a public data release. So that's all I had. If there are any questions, I'd be happy to take them.
Yes, thank you, Catherine. We do have a couple of questions that we have time for. So the first one is, could this method be generalized to other regions of the world? Well contamination of various types is a huge problem, of course, cholera, arsenic, and Bangladesh and other places. So could the method be generalized to other parts of the world?
Oh, definitely. You just need your predictor variables for that region, and the XGBoost method is extremely flexible and can be applied to any data set.
Okay. Second question, did you predict nitrate in water table aquifer wells or all domestic wells?
I'm not sure what the difference is between, I'm not sure if I understand the question, but we
Well,
had
maybe that some of the domestic wells might be, let's say, in a confined aquifer, although that's maybe unusual. I'm not sure if that's what the question's asking.
We did weed out where we had indication that there was a confined well. We did remove those. But the depths that we're predicting to, some are confined. I'm sure of that because we just took reported well depths and calculated like a moving median. That's this work by Jim Dignan and Leon Kaufman that will come out pretty soon in the next few weeks and will also be publicly available. But some of those were confined, so yes.
Okay, did you experiment with fitting the model to smaller regions of the US? If so, do the dominant predictors or their effects shapes change regionally?
We didn't fit the model to different regions, but we did look at SHAP for certain aquifers, and the variable importance based on the SHAP does change for the different regions. So the regions that were more contaminated, we saw more of the nitrogen input variables rising to the top of the importance ranking, and things like that. So, but the model was globally fit.
And one last question, can your model be used to define riparian buffers?
I'm not sure. Don't know.
Okay. All right, well, I think we'll leave it at that. Thank you
Thank you.
very much for your excellent presentation.